to FMA 0146 Basic Mathematics. Today, we are going to learn Chapter 6 Differentiation. In Basic Mathematics, we are only cover derivative of a function, techniques of differentiation, then we're going for the higher order derivative, and last but not least is the implicit differentiation. So actually, what is a introduction? What is a derivative? Derivative in mathematics is the rate of change of a function with respect to a variable. So over here, in mathematics, normally we say that the rate of change, we are using the delta. So then what is a delta? Delta, basically we say that is the difference of the two nearby variables. So we have y2 minus y1, x2 minus x1. And in geometrically, the derivation of a function can be interpreted as the slope of the function. So if you see that on this curve, we have different slope at different points. The notations for the derivation of a function, we can use one is called the derivative of y with respect to x. So we have the dy dx. The dx at the below is very important because we are telling people which variable you are differentiating towards to. Okay, or at certain excuse me, at certain time we can use the y prime. Means that on the y at the top there we have a one a prime on the top over here, or we can use f prime of x. So we have a f prime x. Okay, and now over here is just like it's a terms that is when we write dy dx means it's a noun or it's a name. Okay, and then d over dx means it's an action. So you are taking the derivative with respect to the x. Now we are looking. Okay, so over here we are at the last of this chapter. We're going for the higher order differentiation. So for example, when I have a y, so when I take the first derivatives towards y, so it's d over dx. Then after that, I'm going to differentiate this particular first order again. So I'm going to differentiate this first order again. So if you look over here, I have 2d, so it's d2, and my dx is repeated. You can say that it's in this way, dx power of 2, and your y is over here. But the thing is, we quite of lazy to write, or it's more convenient that we drop the bracket. So finally, the second order, we have d square y over dx square. Or the more convenient way is we write f double prime. Now, notation for the derivative of a function. Differentiation respect to the requested variable in the question. Basically, whenever equation they give it to us, for example over here, we have y equals to x cubed plus 2 theta. Now, if we know that is y is an variable, x is another variable, and theta also can be another variable. So, if people didn't tell you which are the variable, so you can say that y, x, and theta are your variable. But when we're going to differentiate, you must tell people that is which alphabet you want to, or which variable you want to differentiate respect to. So for example here, that is, it said that I'm going to differentiate y towards x. So this is your y and this is your x. So now the theta is already become a constant. Okay. So, and then after that, so how we going to differentiate? Okay. So this is the equal sign. So my left hand side is y. So my left hand side is y, and then my right hand side have my x, and this one is now temporarily is become my constant. So when people say differentiating this thing, so I'm going to differentiate the left hand side towards y, sorry, differentiate y towards x, and differentiating my right hand side towards x. So after that, because of y consists of x, so you cannot say that this one disappeared. So I have my dy dx, and this one for temporary we accepted that is differentiate x cubed actually is 3x squared and dx over dx, but the thing is dx over dx actually is 1, and over here dx over 2 theta, and later on you will learn that is differentiate this one will become a 0. So now if the question asking you differentiate towards theta, now your x is a constant. Okay, so then you're going to we're going to differentiate towards theta. So now if you learn differentiation, equivalent differentiation, first thing that excuse me, you need to know that is which are the function and which are the variable you wish to differentiate towards to. Now, after that, we have the another one that is not necessary. The question is always dy dx. The question can be dh dx. The question can be dx dy, and so on. And if you look at here, that is the first thing we are normally tends to do is dy dx. Okay, if we tends to do over here is dy dx. If you want to do dy dx, so the right hand side actually is 3 square. And but the thing is, the question asking for dx dy, we can flip this thing to we can flip this thing. This one will become 1 over 3x squared. Or we can differentiate the y towards y. So I have a dy over dy equals to 3x squared dy dx. And I rearrange over here, I have my dx dy equals to, oh sorry, this one is a dx dy, and then we arrange, I have this answer. Or you can rewrite y equals to x cubed plus 2 in the form of x equals to y minus 2, 1 over 3, and you find the dx dy. So if you look at here, for a simple example, y equals to x cubed plus 2, you have 3 different ways to solve the question. So differentiation is not a question or not a part that is people telling you you only have a one way to solve a question. You can have, most of the time you have more than one to solve a questions. Okay, now we move into the first part of our derivations. Okay, so we would like to differentiate a constant. So over here, there is a note saying that is, if the derivative of a function is low, and then for a constant function, the derivative must be 0. So now, for example, if you have an equation for a line y equals to 3. So if you look at here, the slope of this y equals to 3 is always 0. So now we have, if we want to find differentiation for a constant, or we can say it's a number, is equals to 0. And over here, there is a remark saying that is a constant is a number on its own or sometimes a letter. So means it can be a, can be k, can be pi, or e2. Okay, so e2 actually is a thing that is quite nasty, because it can be have a friend name is exponent 2x. Exponent 2x, when we have a variable x over here, it means that e power of 2x is a function. E power of 2 actually is a number, or the another alphabet we used to we always can use is z, or sometimes is a t, okay, to stand for a fixed number. Now, the second one is derivative of power function. What is called power function? Any function, okay, can be write into a power form. Over here, before we go for the chain rule, so now the most basic is the one polynomial, excuse me, with a power of n. Okay, so how we going to do is we bring the n going to in front. So I have an n, and n being the number being minus 1. Okay, this one is the standard derivative for the polynomial or something with a using the power rule. So now we look at the first example, fx equals to x power of 4. So the 4 we bring to in front is 4. 4 minus 1 is 3. So another example is x power of 8. So I push my 8 to in front, so it's 8. And then after that, my 8 minus 1 is 7. So how about some numbers? Okay, for example, if I have my gx equals to square root of x. So what is the square root of x? If we change it into the index, is x1 over 2. So what is my g prime x? So I bring the half in front, x half minus 1. So finally, I have 1 over 2, x1 over 2. If you like, you can always change back the x1 over 2 into the third form. So it will become 1 over 2 third x. Okay, so now, or there is another example. We have an, let's say I have an hx equals to 1 over x squared. So this one, if you see that is, I can easily change the index into a negative. So it's x power of negative. So how am I going to differentiate it? So negative 2, bring in front. X, remember, it's always minus 1. So you're going to have negative 2, x minus 3. And you can bring the negative 3 to the underneath. So it's become x over 3. So maybe you will ask that, is it compulsory from changing from the negative index into a positive index? The answer is no. It really depends on the requirement of the question. If the question never said that you must write in a positive index, so you can leave your answer in a negative index. The next thing we're going to see that over here is derivative of a constant times a function. Okay, so now if you look at here, the k over here actually is a constant. Constant on the layman words is called number. So what we do is we can take the constant out from your derivation. So now, for example, if I want to differentiate 7x power of 5, I can bring my 7 out from here. So I'm going to differentiate 7 d over dx, x power of 5. And we learned that is I push the 5 in front. So x 5 minus 1. So I have a 35 x power of 4. Most of the time, we didn't write this one for the second time. So what we do that is, we know that is we just need to multiply of this number. So what we do that, we straight away bring the 5 to in front. So 7 times 5, and then the 5 minus 1 is because equals to 4. So I have a 35 power of x power of 4. And then now I have the derivation of the sum and difference. Okay, power. Okay, sum and the difference. Okay, so over here, what do you mean by the sum and the difference? So I have two different functions. For example, we have a u and I have a v. These two are two different functions. I can separate them. Okay, so now we look at y equals to x power 4. This one is a polynomial power of 4, and this one is the linear. So what we can do that is, according to this theorem is, if I want to differentiate this y, means that I can separate them, differentiate them separately. Okay, so differentiate x power of 4 and differentiate 12x. So differentiate x power of 4 is I push the 4 in front. So I have an x cubed plus differentiate 12x, it become a 12. Okay, so how about this one? If a minus is the same thing, if I want to differentiate y, so I can differentiate x power of 4 minus 2, I factor the 2 out, differentiate x squared and differentiate 2. And we learned from the previous slide, differentiate constant is 0. And then differentiate x power 4, I push the 4 in front, so I have 4. And then 4 minus 1 is 3, so 4x power of 3. And minus these 2 bring in front is a 4 power of x. Okay, now maybe some of the book, they will write that as a 4x and then they have an x squared minus 1. Or maybe they go even far beyond is a 4x, x plus 1, x minus 1. Yeah. But the thing is, this one, the final answer is useful where, in the chapter 7. Maybe we want to use it to find the extremum point. But for this particular chapter, we no need to factor them in the simplest form. So you can just left your answer in the 4x cubed minus 4x. Okay. And then maybe some of you will ask, is it compulsory to write this sentence? No. This one is only to show you that is how we're going to use this particular formula. Okay, now we're going for the last of the syllabus of your vocabulary for your derivative. The next one is the logarithm and the exponential. Okay, so for the logarithm, if you want, this one is a special case where that if you want to differentiate L and X, so the X is going to underneath, so you have 1 over X. And then for the exponent, exponent is the most special function, that is how many times you differentiate each towards, it will remain the same. Okay, so then this one, your vocabulary for the differentiation is done. Okay, don't compare with some others. They were going to learn trigonometric function, okay, or the hyperbolic function. They are not in your syllabus. Now, we look at one thing is the first technique we learn here is called derivative of a composite function, or you need to use a chain rule. So over here, the statement said that is consider excuse me, consider a function in the form of y. You have fu, so the u over here of originally we have a composite function fgx. So I'm going to replace my g using a u. Later on we are going to differentiate, and the differentiation here we are based on this dy du. Okay, what does it mean? So if I want to differentiate a function with a composite function, means that this is a composite function where I have an f not g. So how am I going to differentiate this thing is I let alphabet u equals to gx. So my f not g is become fu. And later on, we look for df du and du dx. Later on, use this particular chain rule formula. So we have du, df du, du dx. Okay, maybe you quite blur. What does this mean? So we look at the first example. Okay, now we learned in the previous slide that is if I differentiate any power rule, so x power of n, my n is going to in front and x n minus 1. But in this particular case, this is not an x, this is 2x plus 1. Or sometimes we have more others, we can have some others more complicated function. So what we can do that is according to this chain rule is I let u equals to 2x plus 1. Okay, whatever. Okay, you remember this one is the power, so this is the power. So we try to rewrite 2x plus 1 look like x power of n. So what we're going to do is So now u equals to 2x plus 1. So my fx is become fu, and this 2x plus 1 is become u power of 4. Okay, so after that, now from here, okay, because we learn from this particular df dx, okay, so we learn df dx, so equals to df, okay, because this f now is related to u, so I have df du, and then this u is related to x, so I have du dx. Okay, now if you see that if you cancel or simplify du and this du, so you have a df du. So this one is particular we mention as a chain rule. Okay, now differentiate 2x plus 1, so we have a du dx, so this one is 2, and differentiate df towards du equals to 4u du dx. Okay, now maybe you ask, why is du, d for u, okay, sorry, this is for u power of 3, sorry, so df du is for u power of 3. Okay, now, and then what is the next thing you want to do is df dx. Okay, so df du is this one, so I have 4u power of 3, and then multiplied with 2. So finally, I have an 8u3, and but because of this variable is x, I need to change back my u, so I have u, and then I have 2x plus 1 power of 3. Okay, now, so this one is called a chain rule. Okay, now, maybe some of the student who already in my class, I already taught that is, you are not necessary to use the chain rule, but we applying the chain rule and in a unwritten form. So means that from this one, I know that over here, the most powerful people is power of 4. And then I using this a particular power rule. So my f prime x is equals to 4, push it in front, okay, and this one of copy back, 4 minus 1 actually is 3, and because of there is a someone inside here, so I differentiate 2x plus 1 actually is 2, so it's 8, 2x plus 1 power 3. So maybe you will see that is any different, there's no different. We are applying the chain rule, but the thing without writing this one formally. If you prefer to write it down, you can proceed with the first part of this slide. If you are confident enough that is, you can straight away using the second part of this. Okay. Now, and then after that, we now, because of we already been introduced with the chain rule, so we look at our logarithm again. Okay, so now over here it said that is, if your function of the logarithm has been written as L and U, so what you need to do that is when you derive it first, so the U will go to underneath, and then you differentiate the U. Okay, so what it means by here, okay, so now my u over here is x squared plus 2. Okay, so the according to the formula say y prime, whatever over here is going to, or my u is going down, x squared plus 2. Okay, don't forget our beloved 3. Okay, now, after that, it said according to here is you need to differentiate. So differentiate of x squared. So u prime actually is 2x. So I write here. And now you look at this thing. Can you simplify? No. When it cannot be simplified, so this is your answer. Okay. Now, how about exponent? Exponent are the same. Okay, exponent, as I said, is always the special. It will never change its form. So, according to this one, is saying that is first, the EU, the exponent U, you copy back. After that, you differentiate it. So, this one, remember, this one is my U. Okay, we compare here, so this one is U. So my u is x squared plus 1. So my u prime actually is 2x. So differentiation of here is y prime. The 3 we take out. So our beloved exponent, x squared plus 1, you must copy back and multiply with this one is 2x. So finally, we have a 6x exponent x squared plus 1. Okay, now, maybe some of you will ask that is, according to over here, is u prime x at the back. So why am I putting the 2x in front? Because for me, that is, writing in front is more convenient to know that is this one is two different function rather than at the back. Okay. Now we look at the first example over here. We have y equals to 1 over 2x plus 1 power of 4. Okay, now what we can do that is, just now we learned that is, we can bring this index into up here. So y equals to 2x plus 1 negative 4. So according to the chain rule, so first thing, I push the negative 4 in front. After that, this one I copy back. So this one minus 1 is become minus 4. And differentiate inner is 2. So finally, I get negative 8. 2x plus 1 negative 5. And asking yourself, this 8, can you bring it inside? No, because this is minus 5. Anything with a power, you cannot bring the outer inside the power. Okay, so whoever love to use chain rule, so you can always use that is, start from here, y equals to 2x plus 1 negative 4. So you let your u equals to 2x plus 1. U prime actually is 2. So y equals to u negative 4. So dy du equals to negative 4 u negative 5. So you use your dy dx equals to dy du multiply du dx. So you're going to have negative 4 u negative 5 multiplied with 2. And then don't forget, change back the u. So I have negative 8, and then my u is 2x plus 1 negative 5. If you look at these two answers, they are exactly the same. So regardless which method you use, you will having the same answer. So how about y equals to exponent negative x? So as I said that exponent is the most special. What we always do, first thing, copy it back. And I always will left some space over here to write the differentiation of this one. Differentiate of negative half x actually is negative half. Okay, so settle. Then now I have we go to a logarithm. Okay, you need to know one thing. Logarithm is the most, okay, compared to exponent, logarithm have a special features, that is, they have a theory that, they have the rules that ln pq equals to ln p plus ln q, and I have a ln p over q equals to ln p minus ln q, and the last one is ln p power of q. I can bring the q down, is ln p. So now, because of ln, the natural logarithm have a special features of this. So sometimes when any question involving the logarithm, you have a special way to do it. So for example of this, y equals to ln 3x, we learned from a previous slide that is, when I want to differentiate this one, the one inside the ln, I bring it down, is 3x, and differentiate 3x actually is 3, and after simplify is 1 over x. Okay. At the same time, I can use the features over here, ln pq equals to ln p plus ln q. So my y actually is ln 3 plus ln x. Now, y prime, differentiate ln 3 actually is 0. And y, because ln 3 is a number or is a constant. And differentiate ln x, we learned that is 1 over x. So if you look at here, the answer are the same. Now, let us look at the second technique. It's called derivative of a product, or we're going to use the something called product rule to solve a function which is in the form of multiply of two different function. So now the formula given by this product rule is, if you want to differentiate the UV, two different function, and then the formula is UV prime plus VU prime. So what is the U and what is the V over here? So let us look at the first question over here. So we want to differentiate two different functions. Let's say it's x squared plus 3 and 2x cubed plus 5x. Okay. And over here, if we over this one, the first one function I represent it as my u, and the second one I represent it as my v. So I have, according to this formula, is u dv. So my u is x squared plus 3 and my v is 2x cubed plus 5. So what is the dv? dv actually is differentiate of my v. So I have 2x cubed plus 5x. So I differentiate this one, I will get 6x squared plus 5. And I want to differentiate u, actually I going to get 2x. So I return here. So if you look at here, so my differentiation is almost complete. But because of this particular question, we can further expand them. So if we keep on expanding, so we have this 6 of this one, and then we rearrange them, so we will get 6x power of 4 plus 33x squared plus 15. But some of the students will think that is, why don't I expand it at expand these two functions? So if you expanding, so you will get, for example, x squared multiplied by 2x cubed, actually I have 2x5. So x squared multiplied by 5x, so I have 5x cubed, and so on. So the other two. And then after that, I rearrange back, because of x power of 3, I have 5 and 6, so I have an 11. So now if I differentiate this one, I have a 10x power 4 plus 33x squared plus 50. So if you look at here, the final answer are the same. So maybe you said that is, instead of I using this formula, and this one is a lot simpler. Yeah, I agree with you, because this one is very easy to expand. So now if you have this question, you have this one, x squared plus 3 power of 2, yeah, and you can easily to expand. But the thing is, this one is power of 5. How you would like to expand? And there are many function that is you are not allowed you to expand. So then you need the something called product group. Okay, so now how am I going to solve this one? So now, without further ado, that is the first one, we have two different functions here. One is with the power of 2, and another one is power of 5. So the one power of 2, I will always take the first one as my u. So it's u equals to x squared plus 3 and power of 2. And then, excuse me, my v is 2x cubed plus 5x power of 5. Now, what you need to do, both function we differentiate. So I use u prime. So then 2 bring in front, x squared plus 3. 2 minus 1 is 1, and differentiate inside is 2x. So finally, u prime is 4x, x squared plus 3. And then how about my v prime? So push the 5 in front, 2x cubed plus 5x, this is power of 4, and don't forget differentiate inside is 6x squared plus 5. So finally, this one, if you want to multiply in, also can. If not, we just leave it alone. Okay, now we plug it into the formula, is uv prime plus vu prime. So what is my uv prime? Is this multiply here. So I have a 5, and then I have my x power of 2 plus 3 power of 2, and then this one is 2x cubed plus 5x power of 4, and I have 6 squared plus 5. This is only for the uv prime. And then what is my vu prime? And remember, this is a plus. What is my vu prime is this one. So I have my 4x, x squared, 4x, x squared plus 3, and 2x cubed plus 5x power of 5. And you cannot stop here because there are so many things are in common. So what you need to do is you need to plug out the common factor. So what are the common factor here? If you look at it, this is a 5, this is 4, there's no common factor. And over here have an x, over here there's no x, so there's a settle. And then, but the thing is, I have x squared plus 3. This is x squared plus 3. So I factor out x squared plus 3. After that, this one is a 5. This one is a 4. So I factor 2x cubed plus 5x power of 4. Okay, and now we need to make sure the balance written back. So with a 5, 6x squared plus 5, and then plus with 4x and 2x cubed plus 5x. Okay, now if you see over here, we have a complete factoring them. Okay, but the thing is now we can see that over here we still can further simplify. But the thing is, if you look at it, nothing for you to be simplified anymore. So you can leave your answer over here like this. Okay, then as I say, we have another one example of a product or multiply of two different functions is set x and exponent minus x. This question you not allow you to expand it. You have nothing to be expand, you nothing to be multiply. So you anyhow you need to use the product rule. So what you need to do is the first one is always your u. So u equals to set x, or we can write as an x power of 1 over 2. And my v actually is exponent minus x. So u prime half x minus half. And then this one is v prime exponents, copy back, and differentiate minus x actually is minus 1. Okay, and now what is my y prime? uv prime plus vu prime. So uv prime plus vu prime. So I have half minus e minus x plus vu prime, and this one is half x negative half and e minus x. If you like, you can factor out the exponent minus x, and then here is half plus 1 over 2 x 1 over 2. Maybe some of you more interested, then you say that is what is the normally the book will not leave your answer in this way. What they will do is they will further expand it. So this one is set x plus 1 over 2 set x, and what they will do that is they will be equate the denominator, so it's ex. This one is x plus 1 over 2 set x, and finally they will give you the answer is that ex over 2 set x x plus 1. And maybe some of you saying that is what happened if you leave your answer over here? I will accept it because the question never said that is you cannot leave your answer in a negative index. Now we look at the third technique. It's called quotient rule. Quotient rule is contrary with the product rule. Quotient rule means that you write your equation, your question in a quotient way. So it means that you have u over v. The formula over here actually is, if you want to differentiate u over v, actually is uv prime minus vu prime over v squared. Okay. Now, if a product rule, the choice of you want to choose which one is u, which one is v, it doesn't matter. But the thing is, for the quotient rule, the one in the denominator must be a v. You have no other choice. Okay, so now we look at the one of the example. Is we have an x cubed plus 2x power 4 minus 1 over 2x plus 3. If you look at this question, you have no way to simplify it, and maybe even there is no way you can factor it. So now what we do that is we just using the formula, and the nominator u is become x cubed plus 2x4 minus 1, and my v must be my denominator is 2x plus 3. So u prime 3x squared plus 8x power of 3, and my v prime actually is 2. So now applying to the formula, y prime is okay, v squared vu prime minus uv prime. So first thing, you will always draw a longer line to have a numerator and denominator. I always will write my v squares first. So my v is 2x plus 3 square. Don't ever try to expand 2x plus 3 here. Okay, now, and then formula say is vu prime. So I have this one multiplied with this. So it's 2x plus 3 multiplied with 3x squared plus 8x cubed, and then minus v prime, so I have a 2, and then x cubed plus 2x4 minus 1. Okay, unfortunately here you need to be expand it. Okay, you need to expand it. So now over here I have a 6x cubed plus 16x power 4 plus 9x squared plus 24x cubed, and expand here 2x power of 3, and don't forget this is minus, so it's minus 4x power 4, and the last one is plus 2, and the denominator still the same, never expand it. Okay, now here is an x cube, this one is an x cube, and this one is an x cube. So what you need to do, 6 plus 24 is 30. 30 minus 2 actually is 28 x cubed. And then this is x power 4, and this is x power 4. And then 16 minus 4 actually is 12 x power 4. And then the x squared, there is no taker, and the 2 no taker. And don't forget our denominator. Okay, so solve your problem. Okay, now maybe some of you who is weak in algebra, then maybe you will say that is, can you leave your answer here? Yeah, you can leave your answer here, but you will lose some marks for the expansion and the final answer. So now that's why if you look at here, so this one is the final answer from the previous question. Okay, now we go for the higher order derivative. So what is the higher order derivative? So you differentiate the thing one time and the two times. Okay. So higher order, so this is the first derivative of the thing. After that, this is the second derivative. So we have a double prime. And then after that, if you look at here, this is 3 prime. And we write here as a 3 here. Okay, and the last one over here, this one is y power 4, and this one is 4. Okay, so now let's see, we have a dy, they give you y equals to x squared plus 3 power of 2, and they look for the third derivative. Okay, this question, my advice is, because they are looking for higher order, so my advice is this one expand it, because when I expand, this one is x power 4 plus 6x squared plus 9. So when I find the first derivative dy dx, so I differentiate, is 4x cubed plus 12x, and then after that second derivative dx d square y dx square equals to 12x squared plus 12, and the finally I differentiate again, so I will get 24x. Okay, if you're not using expansion, you will cut yourself into a product rule. Okay, now what I want to emphasize over here is the way how you want to write this notation. Okay, from y, I have d differentiate y towards x. Okay, after that I differentiate this again. Okay, so I have a 2d, so I will have 2d and y, so my dx is square. And I differentiate this again, so d over dx, so d square y dx square. So I have how many d? I have 3d, and then my dx now is 3, so this is the way to write. If you don't not prefer to write as a dy over dx, you can always say it's y prime, y double prime, y triple prime. That's all. Okay. Okay, so this is the answer. Okay, now we go for the last one over here in your chapter 6. Is called implicit differentiation. Okay, what is implicit? Implicit means that, okay, so before that we go for explicit function first. So explicit function is a function you can write y as a function of x. So means that your title is a y, and then all the variable x is on the right hand side. Anything cannot write in the form of y equals to x, so it is called implicit. So for example, we over here we have xy equals to exponent ay squared plus bx. Either you use the logarithm and so on. You cannot rewrite this one in the form of y equals to something. But there are certain equations or certain function which that easily you can be rewrite into explicit. For example, I have an x cubed y plus 2y. I factor the y out, so I have an x cubed plus 2 equals to y, and I bring the x cubed plus 2 to the other side. So I have this one from a so-called implicit, I able change it into a explicit. Now, so how we are going to differentiate an implicit function? Okay, remember, not every implicit can written in as an explicit. So you need to know how to differentiate an implicit function. So it's quite simple. That is, whenever, okay, so recall back, when you have y equals to x power of 3, whenever you see a y, we write as a dy dx, and then we differentiate 3x squared as 3x squared. Actually, there is something called is dx over dx, but this one we never write, so we have only 3x squared. So now we mark our friend y. There is a y over here. This is one is an x. So now whenever you see y, we have a dy dx. So, and then this equal, and you can't do anything on your equal, so it's equal, differentiate x cubed is 3x squared. Okay, now how are we going to differentiate y squared? You just treat them as a differentiating a power, so the 2 bring in front. So y2 minus 1 is 1, and then differentiate y is dy dx. And then because of the question asking for dy dx, what you need to do is you need to rearrange this thing. So I bring this one to the other side. So I have my dy dx 1 minus 2y and equals to 3x squared, and I bring this one to the other side, so I have a 3x squared over 1 minus 2y. And you will notice that is your dy dx consists of variable of x and the variable of y. So normally when people looking at dy dx is in the form of x and y, we know that this one is an implicit function. So now this is the second example. If we want to differentiate xy plus y plus x, ln 2x minus ey. Okay, now we need to identify where is our y, and y, and y. And then this one is my x, this is my x, and this is my x. Okay, now, if you notice that is the first term xy, you have two different arrows pointing to that function. So when you have two arrows pointing to one term, means that you need to solve it using product rule. So I will need to use the product rule is uv prime plus vu prime. So now I will take the first one x as my u and then my v as a y. So u prime equals to 1 and v prime actually you can write as dy dx or you can write as a y prime. And I substitute inside here u v prime and v u prime. So I will have x y prime plus y. Okay. And then differentiate y as we said, that is we will get dy dx or we can get y prime, and x will get 1, and then differentiate L and x will get 1 over x, and differentiate of exponent y. First thing, remember, copy back EY, and then differentiate y actually is dy dx. So we have all 1, 2, 3, 4, 5 terms separately differentiate. So actually what we always do, that is we combine them back, xy prime plus y and so on. And remember to collect them back because the question asking to find dy dx, collect them back, and then this is your final answer. Okay. And then now we look at one thing. Okay, so this one is my x, this is my x, and this is my y, and this is my y. So this question is similar to the previous example. Which is the first term on the left hand side? We consist of two arrows, so means that we need to use product rule. So okay, if you see that is we have a plenty of space. So I move this part, okay, I underline this part over here. So I will solve my differentiation of x squared y cubed on my left hand side. So here I need u equals to x squared, my v equals to y cubed. So u prime equals to 2x, v prime equals to 3x plus power of 2 dy dx. Don't forget, whenever you see a y, you get a dy dx. And differentiate of this one, you will get uv prime plus u prime. So I will get my answer is 3x squared y squared dy dx plus 2x y cubed. I'm going to substitute over here. So it's 3x squared y squared dy dx plus 2x y cubed. And don't forget that is equal. Differentiate 2x is 2 and differentiate y actually is 3 dy dx. Because of the question asking for dy dx, I need to collect them back. Okay, so I bring it to left hand side. So I have my dy dx. So 3x squared y squared minus 3 and 2. This one move here plus 2xy cubed. And finally, my dy dx equals to 2 plus 2xy cubed over 3x squared y squared minus 3. Done. Okay. Now, or the second one, over here, we have evaluate y prime at the given value. Okay, so this one, here, this is your y, this one is your x. So the right hand side need a uv. Okay, so my right hand y sub x. Actually, the question I can change it to y x 1 power of x. So my u actually is y. So my my u prime is dy dx. My v is x1 over 2. V prime is 1 over 2. X minus 1 over 2. And now differentiate 2y actually is 2y dy dx minus differentiate x actually is 1 equal. Okay, differentiate of this one, actually I already know that I can cross product it. So I have a half y x negative 1 over 2 and multiplied with, plus with x 1 over 2 dy dx. Because of this particular question asking, evaluate y prime at the given value where your x equals to 4, your y equals to 3. So means that I no need to collect my dy dx. I directly substitute here 2. Whenever I see y is 3, so dy dx minus 1 half 3, and then this one is 1 over sub 4, and then plus sub 4 dy dx, and sub 4 actually is 2. So now I have 6 dy dx minus 1 equals to 6, okay, this one, actually is 3 over 4, and then plus 2 dy dx, and I collect them back. 4 dy dx actually is 1 plus 3 over 4, and this one actually is 5 is sorry, 4 is 7 over 4. Finally, dy dx equals to 7 over 16. That's all. Okay.